to working physicists, quantum field theory is the most important thing we know. The point is that when we talk about physics to non-physicists, when we popularize it, we never mention quantum field theory. We talk about particle physics, we talk about relativity, we talk about quantum mechanics. Heck, we talk about string theory and the multiverse and the anthropic principle, but we think that quantum field theory, yeah, it's too much to bother about. Very good. This picture that we put together in 1935 remains true to this day, and it will remain true forever. It will always be true that people like you and me are made of atoms that are made of electrons, protons, and neutrons. We've added to the picture, such so that by the 1980s, here is the kind of picture we had. So we knew that there are still protons and neutrons, but we know they're not elementary particles. Protons and neutrons, the nucleons, the stuff that make up the nucleus, are actually made of smaller particles called quarks. We had the up quark, the down quark, and there's two ups and a down in a proton, two downs and an up in a neutron. And if you have a little bit of physics education, you might have faced this point where your teacher, your professor is telling you, is light or is matter, are electrons particles or waves? This is some sort of dichotomy you want to resolve. And I'll bet you, 10 to 1 odds, they didn't tell you the answer. The answer is it's waves. You need to understand what is going on. You actually need to give up a little bit on the notion of particles.
You know, the ancient Greeks understood this thousands of years ago. Walter Russell understood this, 80 years ago. Nikola Tesla understood this. I'm going to quote the idiot moron Einstein on light. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, the particle and wave theory of light, neither of them fully explains the phenomenon of light, but together they do. And here we have the wave-particle duality. Now here's something else, too. Not only does Mother Nature not deal in particles, she deals in pressures and fields, and everything is fields, and fields are sure the hell, sure the F to the F squared, not particles.
So what is a field? A field is just something that fills space, that takes on a value everywhere. So the temperature of the air in this room is a field. At every point in space, there's a temperature value. But temperature is obviously not fundamental. It's a property of the air.
I will give any one of you $1 million right now if you can go find in any book in science the true definition of a field in principle, not as expressions in vectors over a period of time. All Maxwellian field equations are vectors over a period of time measured as effect. I'm talking about a field in principle. Okay, if you understand what the hell that means, then you're pretty smart.
By the 19th century, we had a picture of physics where matter, stuff, was made of particles, atoms. Atoms became sort of accepted by the modern scientific community in the 19th century. And forces, we said, are made of fields. The electromagnetic field was understood in the 19th century, as well as the gravitational field. The 20th century was more absolutist in its leanings. The 20th century comes along and says, you know what? That particle stuff is overrated. Actually, everything is made of fields. You don't need to separately talk about matter made of particles and forces made of fields. All you need are fields. That should puzzle you a little bit. How can it be? I'm telling you, and I'm not going to back off this later, this podium right in front of me is made of fields. Little vibrating numbers at every point in space are what make up this podium, are what make up me and what make up you. But we feel solid, right? How can it possibly be that something as tangible and solid as ourselves or the Earth can be made of vibrations or oscillations or gradients in fields filling space? And so quantum mechanics says this idea that there's an electron, a particle, and it has a position and it has a velocity is just wrong. It's not that we can't measure the position and the velocity. It's that there is no such thing as the position and the velocity. What there is a wave function.
The nonsense of a wave, packet, and the photon is a misunderstanding of the dielectric energy carried proportional to the frequency of the bounding electromagnetism with its internal coaxial radial charge carrying conductor, the dielectric. The electromagnetic components are merely byproducts of the dielectro-electromagnetic geometry incorrectly thought of as electromagnetic in nature.
Fields mean that the fundamental ingredients of reality are not particles. They're things that take on values everywhere throughout space. But quantum mechanics says when you look at the fields, you don't necessarily see this nice, smooth, undulating fieldness of them. If the fields are only vibrating a little bit, when you look at them, they resolve into individual packets of energy, and it is those packets of energy that we call particles. So particles are just small vibrations in quantum fields.
A wave is not what something is. A wave is what something does. You know, hey, I'm waving. Look, I see waving here.
And what happens is that the empty space before your eyes right now is full of many different kinds of elementary fields that make up the universe. Not just the electromagnetic field, the gravitational field, etc. For every particle that we mentioned in the flow chart, there is a field. There's a W boson field, there's an electron field, there's an up quark field, there's a muon neutrino field, and so forth. And these fields talk to each other. They interact. They're rubbing shoulders next to each other, and one vibrating field can affect the other ones. It can give its vibrations away to the other fields around it. So you have the W boson vibrating. It can transfer its energy into vibrations in the electron field and the antineutrino field. So now it makes perfect sense that particles change into each other, create each other, destroy each other, annihilate. It's just fields vibrating in different ways, transferring their energy from one field to another. So that was the quantum field theory lecture. I hope all that's perfectly clear. The homework assignments will be handed out at the end of the lecture. Why did I bother telling you about quantum field theory even though nobody does? Because quantum field theory is important for two things. Why the Higgs boson was such a big deal, and what we can do next now that we've discovered that Higgs boson. All of the other fields that we know about in nature, if you plot the value of the field, remember that's what a field is. It's something that takes on a value everywhere. Well, it hovers around 0 in empty space. If there's a particle there, it'll be vibrating, but most of the time the fields are just sitting there at 0, whether it's an electromagnetic field, the gluon field, the quarks, or whatever. The Higgs field is way up here. Its value in empty space is not 0. So you see the drama of what is being suggested. These guys were saying, no, it's not the weak interactions that are puzzling. It's that you don't understand empty space. It has a field in it that has tangible effects that we can go out and measure. For example, if you poke at it, if you poke this field, you make a particle. We'll call it the Higgs boson. And that's what we've been looking for the 40-some years since the idea was put forward.
Hey, I see waving going on. Yeah, waves of what? That's the question.
So the Higgs boson is what makes life itself possible. That is why discovering it was a big deal.
The real question, if you want to stump the piss out of these morons, and they're atomists is what they are, and an atomist is a moron by definition. A true Platonist knows that if you're an atomist, you're a materialist, and you're a moron. Just ask them what a field is. There's no branch of current science that has ever defined what a field is in principle. None.
But this idea that the world is made of fields, and the fields vibrate, and they all talk to each other, that tells you how to look for new fields. You shake the fields that you know hard enough, they will start the other fields vibrating. What's coming out when you smash particles together is not what was inside the original particles. Remember, what's really going on are vibrating fields, vibrating to beat the band at incredibly high energies, and their mutual vibrations brings new vibrations into existence in other fields.
Fields are sure the hell, sure the F to the F squared, not particles.
So when the Higgs boson pops out of a proton-proton collision, it's not because there was a Higgs boson hiding in the protons, it's because you made it. It's like you smash two Timex watches together and a Rolex pops out. There is no unique signature that says, look, we found the Higgs boson. The Higgs boson never shows up in your detector. It decays. It has a very short lifetime. The lifetime of a Higgs boson is about 1 zeptosecond, which is very short period of time. So that leaves us in a bittersweet reality. The good news is that we understand all of the laws of physics underlying everything that you see around you right now. That is to say, as you go through your life, the things that, unless you're a working particle physicist, as you go through your life just using your eyes, listening with your ears, touching things with your fingers, everything you experience is explained by the physics we now understand, by these atoms and the other elementary particles. And I added to the background here the Higgs boson field. We understand gravity. All the underlying stuff that makes up you, me, the Earth, the sun, the moon, the stars, the podium, your cat. This is all physics we now understand. This does not tell us what happened at the Big Bang. This does not tell us why there's more matter than antimatter in the universe. It does not tell us what the dark matter of the universe is. So we need to go beyond it. We're nowhere near finished it. But if this theory right here fits all of the data we have ever collected in every experiment here on Earth, which it does, how do we move beyond it? We know we're not right. There are experiments outside the Earth that cannot be explained by that theory. There is dark matter in the universe. This is not a simulation. This is data. This is data of looking in one direction of the sky, looking for the perturbations in how light travels from distant galaxies to us, caused by concentrations of dark matter in the universe. This is where the dark matter is. We know it. There's a map of it. It's not just a conjecture. We also know that the standard model of particle physics, the stuff we've discovered in our laboratories, cannot explain the dark matter. There's definitely some kind of particle, some kind of field vibrating out there, and we don't yet know what it is.
Fields are sure the F to the F squared, not particles.
We have found through scientific investigation that this guy was right, that we were made of particles. We know a little bit better now. We're actually made of fields, but the same basic philosophy applies.
Fields are sure the F to the F squared, not particles.
We have this remarkable notion that seems to be true, that you and I, all of us, all of our thoughts and hopes and dreams, are interacting atoms. Atoms moving around in different patterns, governed by the laws of physics, governed by the forces of gravity and electromagnetism, and so forth. The universe was a very, very orderly place when it started, and nobody knows why. So nobody has a very compelling cosmological scenario, in my view, that explains naturally why our universe had such a low entropy at early times. The quantum field theory philosophy says there's not even a particle. What you start with is a field, something that looks wavy, something that fills all of space, like the electromagnetic field or the gravitational field. And then you apply the rules of quantum mechanics to that, and miraculously, what comes out when we look at it are particles. So quantum mechanics says that what you see when you observe the universe comes to us, in very frequent circumstances, in discrete packets, discrete lumps. Even if the underlying reality is smooth, we see it in individual discrete bits. And it's the particles that make up you and me that are the discrete bits we see when we look at fields.
Mother Nature's a crazy hooker on crack with a gigantic bag of magic particles. And everything's just these little particles, and no, everything is fields, and fields are not particles. Instantaneous action at a distance, by its very premise, negates the notion of particles. Instantaneous is IAAD, instantaneous action at a distance. That makes the particle notion of cosmic mechanics an absurdity. It's absolutely freaking impossible.
You mentioned when you were talking about quantum field theory that everyone's kind of heard of like string theory and quantum mechanics and maybe understands the idea that the Higgs gives mass, but nobody really talks about quantum field theory. But you seem to be presenting it as the accepted philosophy and clearly not string theory. So can you say why people don't talk about it as much?
Oh yeah, so when I say no one talks about quantum field theory, if you go to physicists talk to each other about quantum field theory all the time.
I should say I'm a journalist. So
yeah, so we just don't tell you. It's not that we don't talk about quantum field theory, it's that it's not part of the conventional, standard, potted explanation of modern physics when we go to the outside world, right? We talk about relativity, particles, etc. And I think that a lot of it is because other than the Higgs, you could understand particle physics pretty darn well without understanding field theory as long as you just accepted that particles can magically change into each other, that they can bump into each other and transform. If you could believe that, which you shouldn't, but if you did, particle physics kind of makes sense. You smack protons together, blah, blah, blah. It's what we see when we look at the world. It's intuitive. And why bother explaining that really that electron is a vibration in an electron field if you don't get anything out of it? But it is the way the world works. And not only to explain why the Higgs is important, because it's the field that fills space that's doing the work, not the boson. The boson is just a little vibration in the field. But also to explain how we move forward. What is going to be physics beyond quantum field theory? What if, if gravity, the place where quantum field theory is most likely to break down is in our understanding of quantum gravity. And gravity exists. It's important. We need to understand it. And someday we're going to be telling you that, oh, we have a major new discovery. Quantum field theory isn't right. And you're going to say, you never told us that quantum field theory was right. So I think that it's time that we let you in on that little secret.
Let's pretend for a moment that I'm a brand new high school physics student, and my teachers just explained to me how Michelson and Morley have proved that the ether doesn't exist, the reasons for why people needed to look at it, the wonderful experiment they did, and the fact that ether isn't there. Then the student is sitting here listening to you describe the Higgs field. How do you explain to that student that the Higgs field and the ether are not the same? Because he's going to say this sounds suspiciously like the same thing that my teacher said doesn't exist.
Yeah, real high school students never ask that question, actually.
Hi. Let me go back to high school physics. I'm used to thinking that to have a field like a gravitational field, you need a planet, and to have a magnetic field, you need the magnet. But now it sounds like you were saying that, no, fields exist without the particle. Higgs field exists. Does a magnetic field just exist without the magnet, and so on? The gravitational field exists without the planets? Do I have to rethink my thinking?
Yes.
Thanks. How is that possible then? They're just there? The fields.
They're totally just there. So what you're thinking is that there are particles, which are really themselves waves, but okay, let's forget about that for the moment.
Fields are sure the F to the F squared, not particles.
There are sources to fields. An electric field can arise because there is a charged particle sitting there. But there can just be an electric field. There is no, a magnet is something that is a set of moving charges. But there could just be a magnetic field in the universe. The universe has some configuration of all its fields, a certain thing that the magnetic field is doing, and the gravitational field is doing, and the electron field is doing, and the neutrino field is doing. And they're all coupled to each other, and they all obey one big equation. But if I removed from the world all of the charged particles, I could still put an electric field in the world. If I removed from the world everything, I could still have a gravitational wave traveling through empty space. So frequently, the values of fields in the local region that you live in are determined by their sources, but they live independently. Because the Higgs field is like a rock rolling down a hill. The rock rolls down the hill and hits the bottom and it sits there. A rock at the bottom of the hill doesn't spontaneously start jumping up. The Higgs field wants to sit at a point where its energy is low, its potential energy. And then maybe someday it will get the quantum mechanical gumption to sneak over there, and all of the physics in the atoms that make up your body will suddenly discontinuously change, and nothing that we say here or none of your current hopes and dreams will be preserved.
You know what has been a constant throughout history for thousands of years? Is that every branch of science throughout history, I mean all of it, including today, we all think like, oh my God, we got it going on, man. We are like advanced, yeah. And it turns out like 100 years later, depending on history, they look back at the people that were saying that and they go, oh my God, those people are so stupid.